I welcome you all for this lecture series on artificial intelligence and machine learning. In this lecture, we will see the example problem for A star search algorithm, which is that is informed search. Studying the A star search algorithm in informed search is essential because it efficiently finds the optimal path by combining actual cost G of n and heuristic estimates H of n. Unlike uninformed search algorithms, A star uses heuristics to guide the search, reducing the number of explored nodes and improving performance. It guarantees the shortest path when using an admissible and consistent heuristic, making it highly effective in various applications like robotics, AI planning, and network routing. Understanding A star helps in designing intelligent systems that make optimal decisions while minimizing computational cost. We'll see one by one. First, we'll see the what is A star search. A star search is a powerful and widely used algorithm for pathfinding and graph traversal. It is extensively applied in artificial intelligence, robotics, and game development to efficiently determine the shortest path between 2 points. The algorithm intelligently balances actual path costs and heuristic estimates, making it highly efficient in navigating large and complex spaces. Unlike uninformed search algorithm, A star incorporates domain-specific knowledge, allowing it to prioritize promising paths and minimize unnecessary computations. And what are all the key concepts of A star search and how A star search works? We see this A star search working condition in this slide. A star search relies on two fundamental components to find optimal path. The first one is cost to reach the current node G of n. Cost to reach the current node G of n, and this represents the actual accumulated cost from the start node to the current node. It ensures that the algorithm accounts for real distances or costs, and the next step is the key factor is the heuristic estimate to the goal h of n. This is an estimate of remaining cost from the current node to the goal. A good heuristic function helps guide the search that is efficiently. These two values are combined in the evaluation function and is given by f of n. So f of n means evaluation function. It is given by f of n is equal to g of n plus h of n, where f of n determines the priority of each node during exploration. The lower value of f of n, the more promising the path. Next, what is evaluation function? The evaluation function ensures efficient optimal search by combining actual and estimated costs. And the G of n keeps track, no, this G of n keeps track on the of the known cost from the start node to the current node, ensuring accuracy in path selection. And H of n provides an estimated cost from the current node to the goal, helping direct the search toward promising areas. For optimality, the heuristic function must be admissible, meaning it never overestimates the actual cost. A well designed heuristic improves efficiency while guaranteeing correctness. Next, why we use A star search? The advantages of A star searches are A star is widely preferred because of its key advantages. First one is the completeness. It always finds a solution if one exists, making it reliable for pathfinding problems. The next advantage is the optimality. If the heuristic function is admissible, A star guarantees finding the shortest path and efficiency. Compared to uninformed search methods like Digitra's algorithm, A star expands fewer nodes, making it computationally efficient for large graphs and real-time applications. So next, we'll see one example problem for this A star search. Here, this is the root node. Here from A is B and C is connected from A, and from B there are two children D and E. From D, HI and E, two children are connected JK, and similarly C there are two children FG, and from F LM and G N and O. How we are going to apply this A star search in this problem, we'll see step by step. The first step is the, and before going to start the initialization, we should know the values of g of n for each node a, b, up to here. How many nodes are there? A, B, C, D, E, F, G, H, I, J, K, L, M, N, O. So what are all the values of g of n and h of n? And you know, f of n is the evaluation function. It is given by g of n plus h of n. So these are all the values given in terms of table. We'll see one by one each step. The first step is the initialization. See here, what is the node? Here, this is the starting node. So from the starting node, we have to expand the node A. Look at its neighbor. The neighbors are B and C are the neighbors. Here, the A star search starts at node A when with an initial cost of G of A. What is G of A? G of A here is 0. So 0, and so we are writing G of A is equal to 0, and since there is no cost to reach itself, the heuristic estimate of the goal node O is given as, that is G of A, H of A is equal to 6, and leading to a total estimated cost of what is the total estimated cost for this? So here the G of A is 0. Here the G of A value is 0 and H of n value is 6. So G of n plus H of n is equal to 6. So in this case, and the F of n, F of A value was the 6. At this stage, node A is the only entry in the open list. Open list, node A is only available. And while the closed list remains, in this case, the closed list remains the empty. Correct? Marking the beginning of the search process. And the second step, expand node A. So here, if you are expanding this, in first step, start at node A. Second, we have to expand. So if you are expanding, there are two nodes, B and C. So now we have to look into what is the value of G, what is the value of h of n for both B and C, 1 and 4. And if you are evaluating the function 6 and you are adding g of n plus h of n, you are getting the value 6. Here 1 plus 4 is equal to 5. So in this case, if you are expanding this node, which one is giving the minimum cost? Leading f of B is equal to, in this second, f of B is 6 and f of C is the 5. Since node C has the lower, this is the lower value. Node has the lower value. What will happen after this? If it is having the lower value, we have to proceed from this. The cost of C is the 6 with a heuristic estimate of what? 4 plus 1, 5. Since C has the lower f of n than B, it is added to the open list. Where we are adding? We are adding in the open list. It is and then node A is moved to the closed list and B is put on hold. Since it is the f of value is higher than that of C. At this stage, the open list contains B with the f of B is equal to, what is the value? 6. No? Am I right? 6, f of b is equal to 6. Then what you have to concentrate? C with f of c is equal to, here the f of c is equal to 5. While the closed list contain only the node A. In this node, we are putting A into the closed list. Next, step 3. So from B and C, in this case B and C, we found out this is having the minimal value. So we have to expand. We have to stop this and we have to expand the C value. So if you are expand, the third step is the expand node C. Why we are expanding the C? It is having the lowest f of n. So in this case, what is happening? Expand node C, that is lowest f of n. Node C is expanded next as it has the lowest f of n value in the open list. Correct? It will be in the open list. It reveals two neighboring nodes, f and g. The cost to reach f is calculated as g, here in this case, g of s is equal to g of f is 2 and with a heuristic estimate h of s is equal to 3. So if you are looking into 2 plus 3 is equal to 5. Resulting f of f, capital F is equal to 5. Similarly, the cost to reach g is the 2 plus 2 plus 2. The cost is the f of n is the 4. The value of f of g is the 4. Since g has lower f of n value than f, it is added to the open list first. We have to add it into the open list first. And then what will happen? The uploaded open list consists of b. F of b is equal to 6 and f of f is equal to 5. Correct? G with f of g is equal to 4. While the closed list now contains a and the closed list now contains a and c. Next we have to, since we have found out f of g is equal to 4, we are going to expand the node what? F of g. So the next node is the next step is the we have to expand the node G. So in this case, what will happen? The lowest f of n, it has got the lowest f of n. Node G is expanded next as it has the lowest f of n value in the open list. No, open list. It neighbors n and o are evaluated. The cost to reach n is g of n. G of n is what? Here the g of n is equal to 3, h of n is equal to 1. So f of n is equal to 4. So we are getting 4. The cost to reach goal node. So in this case, with a heuristic estimate of h of n is equal to 4 and there is f of n is equal to 4. The cost to reach goal node is O. G of O is equal to, so in this case, G of O. What is the value of G of O? 4. And heuristic estimate is the heuristic estimate. Here it is given it as, in this case, we are proceeding with 0. So 4 plus 0 is equal to what? 4 plus 0 is equal to 4. While the closest list contains A, C, G, and the last step is we have to expand the node. How many children are there for this node A, O? There's no children at all, right? So we have to expand the last node. What is the node? O. This O, we are calling it as what? Goal node. This O is the goal node. Since node A is the goal, the search stops here. The open list still contains nodes B, F, and N, but they are no longer needed as the optimal path has already been determined. The closed list now contains A, C, G, O, making the successful completion of the search. So finally, the last step is the path reconstruction. The final optimal path is determined by tracking back from O. We are tracking back from O. So it will go like this. O to G, G to C. This is the shortest path. O to A. Identifying the shortest path is A to C to G to O. Correct? The total cost to reach this goal is what? What we found out here? F of O is equal to 4. Confirming the efficiency of the A star search algorithm in finding the optimal route by balancing the actual cost and heuristic estimates. And coming into the conclusion, So this is the table format for finding the optimal path. So the studying the A star search algorithm in informed search is essential. Why it is essential? Because it efficiently finds the optimal path by combining actual cost G of n and a heuristic estimate H of n. Unlike informed search algorithms, what will happen? A star uses the heuristic to guide the search, reducing the number of explored nodes and improved performances, which guarantees the shortest path when using an admissible cost heuristics, making it highly effective in various applications, as I've said initially. And this is the table format for finding the f of n value. So here open list, first we are putting A, then we are expanding the node A, B and C we are getting. From this C is the that is having the lowest value. So in this case we are putting this A into the closed node and C is added to the open list first. That is because it has the lower value. F of C is the 5. Then B, f of B is equal to 6, f of f is equal to 5, and g of g equal to. So here, we are putting the C into the closed list. Now G is added to open list first because it has the lowest value. See, lowest value means 4. Similarly, this steps continues till it find out the shortest path. So in this case, the optimal path is what? A to A2, C2, G2, O. So the total cost of the function is 4. And coming into the conclusion, the summary, if you are looking into, A star is powerful and widely used search algorithm that efficiently balances actual cost and heuristic estimates. By intelligently navigating search spaces, it ensures optimal and efficient pathfinding. It is extensively used in AI, robotics, and gaming, demonstrating its practical significance in the real world applications. So, in this presentation, what we have seen is we have explored the A star algorithm, one of the most efficient pathfinding technique used in AI, robotics, and game development mainly. And so these are all the things we have seen it in this slide. Hope everyone understood this A star search. So this search is used to find out the shortest path in an efficient way by using G of n and H of n. Thank you. The remaining things we'll discuss in the next lecture. Thank you once again.